Okay, so now that we have had our discussion about polar coordinates, what do polar coordinates have to do with double integrals? And so the answer to that is sometimes if we have regions that are a little bit weirdly shaped, sometimes it's better for us to switch to polar coordinates and integrate our double integral in polar coordinates than it is to just integrate, what we might say normally, rectangular coordinates. And so this slide here tells us how to do things. And the 2D region you're integrating over is most naturally expressed in terms of bounds in r and theta. Consider switching to polar coordinates to do your double integral. And so now your bounds are theta is running from theta 1 to theta 2. R is running from R1 of theta to R2 of theta. F of R cosine theta, R sine theta, R dr d theta. There's a lot going on here. Let's take a look here. Here, we always put our theta bounds on the outside. These must always be constant bounds. However, our r bounds go on the inside, and we'll be integrating with respect to r first. R bounds may depend on theta. And then your integrand, you replace x with r cosine theta and y with r sine theta. And then we throw in an extra factor of r here. So our dA means a little chunk of area. We usually replace dA with dx dy or dy dx. But when we do it in polar coordinates, we throw in an extra factor of r here. So it's not dr d theta, it's r dr d theta. We'll talk about why, there's a slide in a future video that will say, why do we throw in an r? Okay, so let's start off with a kind of straight down the middle example here. Let's evaluate the double integral over r, where this right here is our r of x plus y. So first off, realize here so this is going to be, this is some kind of like macaroni-shaped region. It's between two circles. It's outside of the circle center of radius 1. It's inside circle of radius 2. It's in the first quadrant here. This would be somewhat difficult to do in rectangular coordinates. If we try to do rectangular coordinates, we'd have to break it up there, do this, integrate over this chunk, and then integrate over this chunk. We'd have to figure out top and bottom functions there, and none of those are going to be nice. But instead realize that our life is going to be way, way, way easy if we express this region in polar coordinates. What's going on? So the inside circle is r is equal to 1, the outside circle is r is equal to 2. Our r bounds, just r goes from 1 to 2. What about theta? Theta runs from 0 to pi over 2. Theta runs from 0 to pi over 2 here. Well, take a look here. All of our bounds are just going to be constants. So this integral is going to equal theta runs from 0 to pi over 2. R runs from 1 to 2 of x plus y. So now we're doing the substitution here. Everywhere we see x, we replace it with r cosine theta plus y. We replace y with r sine theta, and then r dr d theta. Don't forget to throw in that extra factor of r here. And now, this is going to be a relatively straightforward integral to evaluate right now. So, okay, what what happens here, okay, theta runs from 0 to pi over 2. And then the integrand is going to be, let's multiply through by this r. Actually, we can factor out an r here. So we'll have cosine theta plus sine theta times r squared dr d theta. Okay, antiderivative of r squared is going to be r cubed over 3. The theta, okay, plug in r is 1 to r is 2. And so theta runs from 0 to pi over 2 of cosine theta plus sine theta times, this will give us 8/3 minus 1/3 is 7/3. Okay, and so now what is our, we have to do one more integration here. So antiderivative of cosine theta plus sine theta with respect to theta is going to be sine theta minus cosine theta. Plug in, theta runs from 0 to pi over 2. And we get 7/3. Sine of pi over 2 is 1. Cosine of pi over 2 is going to be 0. Minus sine of pi over, sine of 0 is 0. Cosine of 0 is 1. And this ends up as 14/3. And so in this first example here, we can see that by converting to polar coordinates, this region is most naturally expressed in polar coordinates, and we make our life a lot easier right now. This was a relatively straightforward double integration to carry out. It makes our life a lot easier. And we'll be doing a lot more examples of these in succeeding videos.